Welcome back, everyone. In this lecture, we will continue with the definition of normal subgroups, and we will see some characterization of these subgroups. So, motivated from our earlier discussions, so let's recall what we did so far. So, you start with the subgroup H, which is a subgroup of G. So, then look at all these left cosets G modulo H. Okay, this is given by GH, where G in G. So, these are all the set of all left cosets of G. So, we have seen many examples for which this G modulo H naturally becomes a group, okay, with respect to the following multiplication. Okay, if we take G1 and G2 from capital G, and then if we consider these cosets G1 and G2H, so then we actually saw that. So, this becomes group with respect to this new product rule. Okay. So, we want this set of all left cosets to have group structure with respect to this product. Okay. So, that was our motivation. We saw many examples for which this happens. So, but we also saw that when it can naturally happen. Okay. So, for which subgroups this can happen, that is what we want to address. So, our calculation indeed told us. So, if we take G1H and G2H, and then if we use associativity and then try to compute it what it is, then we can see that this is exactly equal to G1H G2H, and then so this will become what is on the left hand side G1 G2H if one can switch this right coset to left coset HG2 equal to G2H. Okay. If we have that property, then we can allow to switch this. So, this becomes G1 G2 H time H, but it is easy to see H time H will be equal. Okay, this is the step that is we are supposed to actually justify, and that step is true if H G2 equal to G2H. So, then we know that H times H, okay, as a subset of G, it will be H. So, that is something I asked you to verify. So, then this equality actually becomes, so G1 G2, so this comes for free. Okay. So, G1 G2 times H. So, this comes for free since H times H is H. Okay. So, naturally the product of these two sets inside capital G, G1H times G2H, that becomes equal to G1 G2H if we have this property. Okay. The left coset corresponding to this G2 should be equal to the right coset corresponding to G2. Okay. So, this is something naturally arises, this condition naturally arises when we demand this G modulo H to have a group structure with respect to this multiplication. Okay. So, this is what somewhat motivates us to define what is called normal subgroups. So, let us see the definition of normal subgroups, and then we will later so in a minute I will give you various characterization of these normal subgroups. Okay. So, first let us define. So, there are many ways to define because there are various characterization of normal subgroups. So, let us take something that we have here. So, let us rewrite this property that we were demanding. So, what it is? So, we want to demand this right coset Hg should be equal to left coset for all G in G. Okay. Because here the G1 and G2 they are chosen two random elements from capital G. So, that is why we have to demand this right coset is equal to left coset for all G in G. But if you really think about it, this is equivalent to saying that if you consider this conjugation, okay, of this H by this G, so G inverse Hg, that must be equal to H for all G in G. Okay. So, this is what motivates us to define this normal subgroups. So, what is normal subgroup? So, here is the definition. So, let us start with H being a subgroup. Okay. So, then H is said to be normal if the following conditions satisfied. What it is? So, whenever you look at this conjugation G inverse Hg, so that should be equal to H for all G in G. So, this is one definition of normal subgroup. Okay. So, as I promised, so here is a theorem that characterizes all possible definitions of normal subgroups. So, let us start with fixing some notation. Let us take n to be a subgroup of G. Okay. So, then we have the following statements. So, the following statements are all equivalent. So, first is the definition of a normal subgroup. So, that is if you take G n G inverse, that should be equal to n for all G in G. So, this is what we took it as definition. But anyway, this can be relaxed as follows. So, G n G inverse, one can demand this to be just a subset of n for all G in G. So, these two statements are equivalent. The third statement, so if you take the left coset and the right coset, so they should be equal for all G in G. Okay. So, these three definitions are equivalent, that is easy to see. So, here is the the fourth definition. So, if you take this G modulo n, so which is the set of all left cosets of G. So, that is let us say G n, where G running from capital G. So, this forms a group. Okay. This is a group with respect to this specific multiplication G1n times G2n is exactly equal to defined to be G1 G2 of n. Okay. So, note that in this multiplication already there is this well defined property. Okay. So, that also one can take it as another definition of this normal subgroup. Okay. So, if we take two different representatives, let us say G1n equal to G1 dash n and then G2n equal to G2n dash for some G1 G1 dash G2 G2 dash, they are elements of G. So, then if you consider this this product, okay, which you want to demand to be the right hand side G1 G2 capital N. So, those things should be equal. So, G1 G2n should be equal to G1 dash G2 dash n. Okay. So, this should be true for all G1 G2 and G1 dash G2 dash. So, this you can take it to be the fifth definition. So, now the most important definition is the fourth one. Okay. So, this G modulo n is indeed a group with respect to this multiplication that we have defined. Okay. So, then again if you think about it, so the second condition indeed says if you conjugate capital N with any element of G. So, this G n G inverse. So, this is called conjugate of capital N with respect to the element G. So, that must be subset of N. Okay. That indeed says if you take any possible conjugate of capital N, that should be inside capital N. but capital N is conjugate to capital N by identity element. So that says capital N is indeed union of all the conjugates of capital N. Okay, so that you can take it to be this definition 6. So N is equal to union Gn G inverse Gn capital G. And if we think about it more, so there is this inner automorphism of G. So given by this element small g in G. Okay, so you fix given capital G, one can define this tau G from capital G to capital G given by x goes to G x G inverse. So then one can verify that this tau G is indeed automorphism of G. So what is automorphism? It is an isomorphism from G to G. Okay, so that is something one can check immediately. So then if you take these tau G, which are all elements of automorphism of G, so that form a subgroup of this automorphism of G, which is called inner automorphism of G. Okay, the inner automorphism of G, which is denoted by the set of all inner automorphism of G. Okay, this is by definition. So this is exactly equal to those tau G where G is coming from G. Okay, so this is a subgroup of automorphism of G. Okay, so automorphism of G we have already seen, it is a group with respect to composition, and this is actually a subgroup. So this is something easy to verify. I will leave it to you to verify. Okay, so if we take these inner automorphisms, then one can rewrite the definition as follows. So you take tau G of capital N, this should be subset of capital N for all G in G. So that means this subgroup capital N is invariant under all inner automorphism of G. Okay, so here is another important characterization which we call it 8. So since this G modulo N actually becomes actually a group, okay, so that actually gives you very natural targeted group. Okay, so in particularly we can have this what is called quotient map from G to G modulo N. Okay, so where you can send any element G to the coset that corresponding to this Gn. Okay, so later we will see actually the definition of homomorphism. Okay, so in particularly it satisfy, so pi of G1 G2 is equal to pi of G1 times pi of G2. So that is the definition of group homomorphism. So it is a map from G to G modulo N such that for any given G1 G2 from capital G, we have pi of G1 G2 equal to pi of G1 times pi of G2. So in particularly one can verify once this G modulo N is a group with respect to this multiplication, then this is indeed a group homomorphism. Okay, so pi is a group homomorphism if G modulo N is a group. Okay, so this is something we will verify later, but this is not that hard to verify. So now with respect to that group homomorphism, one can see that this N that can be realized as kernel of some group homomorphism. Okay, so this is another important characterization. So there exists a group homomorphism, let's call it phi from G to G dash, such that N is nothing but what is called kernel of phi. Okay, so let me explain two things here. So one is the group homomorphism. So group homomorphism, so I waited till this normal subgroup because group homomorphisms are well connected with the normal subgroups. Okay, so indeed so normal subgroups naturally arise from group homomorphisms. So what is group homomorphism? So it is a map, let's say phi from G to G dash. So you have two groups, capital G and capital G dash, and phi is a map from G to G dash. So satisfying the following property. Satisfying phi of G1 G2 should be exactly equal to phi of G1 times phi of G2 for all G1 G2 in capital G. So that means if you take two elements from capital G and then take the product of those two elements in capital G, and this phi maps the product to the product of respective elements in G dash. Okay. So let's draw a picture and then see what happens. So here you have G, and then here you have G dash, and then you have taken element G1 and G2 here, and their product will lie somewhere here. Okay. So then this G1 is mapped to phi of G1 here, and then this G2 is mapped to phi of G2 here. Okay. So then if you look at what happens to this product G1 G2, so then this product also should be mapped to the respective product here, phi of G1 times phi of G2. So this product is happening in G dash. Okay. So that is what phi does. So phi of G1 G2 must be same as phi of G1 times phi of G2. So that is the demanding that we put for group homomorphism. So group homomorphism is happening in the category of groups. So it should preserve the group structure. Basically the morphism that actually preserves the group structure is called group homomorphism. So now what is kernel? The kernel is, so the kernel, it is nothing but those elements inside G, those are mapped to identity inside G dash. Okay. So this is what kernel. So kernel is actually a nice subgroup of this capital G, which is mapped to identity with respect to that group homomorphism. Okay. So let me, before getting into the characterization of normal groups, let me spend a little time explaining some properties of this group homomorphism and the kernel, okay, which is very important. So the very first fact that I would like to actually prove, the kernel is indeed normal subgroup inside G. Okay. You have a group homomorphism, let us say from G to G dash. So this is group homomorphism between capital G to G dash. So then you have the kernel, so which is by definition this is those X in G such that which is mapped to this identity element in G dash. Okay. So our claim is that it is a normal subgroup. So normal subgroups are denoted by this symbol, so tilted this triangle. Okay. So it is actually a means normal subgroup. Okay, let us see how one can prove this. So you start with two elements and then see, we already have this characterizations for subgroups. So if you take two elements x comma y inside this kernel phi, so then kernel phi is a subgroup if and only if the xy inverse, so this is the claim, should be inside the kernel phi. So how do you verify this? So let us see. So if you compute phi of xy inverse, then using the definition of this this group homomorphism, you can see that phi of xy inverse will become phi of x times phi of y inverse. And it is not hard to verify that phi of y inverse must be same as phi of y inverse. Okay, this is something I will leave it to verify. So that is because y into y inverse is identity. Then if you apply the morphism phi, then phi of y into y inverse will be phi of identity, and phi of identity must be identity of G dash. Okay. So let me leave it to you to verify phi of identity of G map to identity of G dash, because identity times identity should be identity. So, that will tell you that phi of identity should be mapped to identity, and phi of Y inverse should be mapped to inverse of phi of Y. So, because of that you can see that phi of x y inverse is equal to phi of x times phi of y inverse, which is same as phi of x times phi of y inverse. So, now you can see that this is exactly equal to, so phi of x, because it is coming from the kernel, so phi of x must be identity. So, this is identity and this is again identity inverse. So, identity time identity inverse is just identity. So, that means x y inverse is inside the kernel of phi. Okay. So, this proves that kernel phi is indeed subgroup of G. So, this is a subgroup. So, now let us verify it is actually a normal subgroup. So, let us use one of the definition. Okay. The very first definition that I gave you, normal if and only if whenever you take this conjugation, so that should be equal to this capital N. Okay. So, now let us consider this element inside inside this conjugation. Okay. Let us fix some G in G and then some X in kernel phi. So, then look at this conjugation G x G inverse. What happens to this? So, because again G x G inverse is just product of 3 elements in a group G and phi is a group homomorphism, this can be rewritten as phi of G times phi of x G inverse, which can be rewritten again phi of G, phi of x, phi of G inverse. But phi of G inverse, as I told before, it is exactly phi of G, phi of x, phi of G inverse. So, now you can see that this phi of x is given to be identity, because x is coming from kernel phi. So, because phi of x is identity G dash, so you substitute there, then you get phi of G x G inverse is equal to phi of G identity G dash phi of G inverse. But now this term identity times anything is itself. So, it is simplified as phi of G times phi of G inverse, which is nothing but identity G dash. So, that means phi of G x G inverse we proved to be identity G dash. So, this means G x G inverse lies inside the kernel phi for all G in G and X in kernel phi. Okay. So, now what we want to prove? We want to prove that G kernel phi G inverse must be equal to kernel phi. So, so far what we have proved? We have proved that G kernel phi G inverse is subset of kernel phi. Okay. For all G in capital G. Okay, this is what we have proved. So, we want to prove the other way. So, let us see how one can prove the other way. Let us start with kernel phi. So, you can write this as something like this. Okay. So, G inverse of G, G inverse times G, because this is going to be just exactly equal to G inverse G kernel phi and then G inverse G. So, now this is just identity, this is just identity. So, which is going to give you kernel phi here. Okay. So, now if you think about it, so this G inverse of G kernel phi G inverse times G is going to be subset of G inverse kernel phi G from this equation, because this is true for all G in G. So, in particularly we have for this fixed G. Okay, fix G in G. So, then we have this. So, now if you think about it, so then what happens? So, this is again subset of kernel phi. Okay. Or one can actually, okay, we wanted to prove the other way. So what we wanted to prove, so let me write the claim. Claim is kernel phi is subset of G kernel phi G inverse, but it is same as saying that you can put minus here and then plus here for all G in G, because the indexing G in G, G inverse in G are same. So in particularly, if you take this term, okay, you can see that kernel of phi, which is equal to this, is subset of G inverse kernel phi G, which is subset of kernel phi. So this implies kernel phi is equal to G inverse kernel phi G. Okay, so this is what we wanted to prove, and this is now true for any fixed G in G, so it should be true for all G in G. So this is something very simple. So this discussion tells you that if you start with any group homomorphism, then the kernel of that group homomorphism must be normal subgroup. Okay, but one of the characterization indeed says that any normal subgroup is indeed comes from kernel of some group homomorphism. Okay, so this is how indeed normal subgroups arises. Okay, so this is, I want you to remember, whenever you take normal subgroup, so they corresponds to kernel of some group homomorphism. Okay, for example from G to G dash. So this dictionary or the characterization of normal subgroup is very, very important. Okay, in practice, if you are interested in proving something is actually a normal subgroup, then I would recommend, okay, try to find a group homomorphism for which it becomes kernel. Okay, so it's very, very important. But again, abstractly speaking, once you have some normal subgroups, so we will see in a minute, in any abelian group, any subgroup will be a normal subgroup. So because of that, you can produce lots of interesting quotients. So these G modulo n, they are called quotient subgroups, quotient groups or factor groups. So you will be able to produce many interesting family of factor groups or quotient groups. Again, both way it's very, very interesting. Okay, so I would actually indeed prove one or two of these characterizations, and then I will leave it to you to check remaining. So maybe I will try to prove this 1 to 4, they are all equivalent. Okay, so once I am done with that, then you can see that, okay, 5 is somewhat hidden in proving 4 is indeed true, equivalent to the definition of normal subgroup, and then 6 and 7, they are indeed definitions. Okay, 8 is actually comes for free once you prove that G modulo n is a group for normal subgroup n, because the converse of 8 we already verified, kernel of any group homomorphism must be normal. Okay, so let me just spend 1 or 2 minutes in explaining the characterization. So let us start with the first definition. Okay, so the very first definition tells, so G n G inverse equal to n for all G in G. So we want to say that this is equivalent to G n G inverse is subset of n for all G in G, and then the third thing, G n is same as n G for all G in G. Okay, so let's prove 1 implies 2. So 1 implies 2 is obvious, because once they are equal, then obviously the subset will be true. Okay, so this is indeed verified immediately. So now what's about 2 implies 3? So for 2 implies 3, let's observe the following. Okay, so 1 if and only if 3 is obvious, 1 if and only if 3. So this is obvious, because if we rewrite Gn equal to Ng, so then if and only if Gn G inverse becomes capital N, and this is true for all G in G, and this is true for all G in G. So this is indeed very obvious statement. So now because of that we will just prove that, okay, 2 implies 3 and then 3 implies 1. 3 implies 1 is obvious, okay. So we will just prove that 2 implies 3 or 2 implies 1 or 1 implies 2 is obvious, okay. So how do you prove 2 implies 1? So as we did before, you consider G inverse N G, okay, and then apply G and G inverse. So note that this is subset of N, so this must be subset of G N G inverse, okay, because G inverse N G by definition is subset of N. So again fix G and G, not a problem. So G inverse N G must be subset of N. So if you apply G inverse conjugate again, then G inverse N G inverse must be subset of G and G inverse. But note that this is exactly equal to G inverse capital N G inverse. So this grouping we are able to do because we have associative law. So then this becomes exactly identity times N times identity, which is N. Okay. So this simply says that N is subset of G and G inverse. Okay, we have the other way, G and G inverse is subset of N. Now we proved that N is subset of G and G inverse, that proves that N equal to G and G inverse. Okay, so this simply proves that all these 3 statements are equivalent. So now using this, we want to actually verify the 4th statement, which is G modulo N is actually a group with respect to this product. Okay. For that we have to verify few things. First is this product that is given here, or the map which is from G modulo N cross G modulo N to G modulo N is actually a well defined map. So that is what part of this phi. Okay. Once you verify it is well defined, then you have to verify with respect to this multiplication G modulo N is indeed becomes a group. For that you have to identify the identity element and given any element the inverse and so on. But those things are somewhat easy. Why? Because the only verification that you are indeed to do is this well definedness. If you take 2 cosets representatives like this, and then if you multiply them, you have to verify they are same. G1 G2 capital N should be G1 G2 inverse, sorry, G1 dash times N. So this is what we have to verify. So given this, we have to verify the product, the corresponding product must be same as the corresponding product. So note that, so G1N, okay, this is equivalent to what? So this is equivalent to G1 dash inverse G1 is in N. Similarly, this is equivalent to G2 dash inverse G2 in capital N. Recall X capital N equal to Y capital N if and only if Y inverse X is in capital N. So this is something we have already proved. 2 left cosets are equal if and only if Y inverse X equal inside N. So now using this you can see that, so this is equivalent to G1 dash G2 dash inverse G1 G2 is being in N. But what is this? This is exactly equal to G2 dash inverse G1 dash inverse G1 and then G2. Okay. So now, so let's do the computation. So we want to prove the product that we have defined on the coset must be actually same. So so let's compute this. So this is indeed okay. So we have to verify. So, since n is normal inside G, we already know that if we take this element, okay, let's take for example this element G1 dash inverse G1, okay. So, this G1 dash inverse G1, this is an element in capital N. So, now if you conjugate with G2 inverse, so G2 dash inverse G1 dash inverse G1 and then G2 dash. If you conjugate with G2 dash, this is again should be N, okay. So, N being normal implies this. So, now from this how do you get this element? So, that is what we have to see. So, this is going to be, now you can rewrite. So, G2 dash inverse G1 dash inverse G1 and then you write G2 dash inverse G2, okay. So, this is going to be just called, this is x. So, this is x times this y, okay. So, x times y. So, where x is this term and y is this term. So, this G2 dash inverse times G2, it is already given to be element in capital N, because these two are same. So, that tells that this xy is indeed element of capital N, because x is in capital N and y is in capital N. So, that means the product xy is in capital N, but which is same as G2 dash inverse G1 dash inverse G1. So, these two gets cancelled and G2. So, which is what there is here, okay. So, this is element of capital N. So, these two cosets being equal, same as saying that these element G2 dash inverse G1 dash inverse times G1 G2 is an element in capital N, okay. So, that means the product that we have defined G1n times G2n is defined to be G1 G2n is indeed well defined product. So, this is well defined product, okay. So, now I will leave it to you to check if you take identity times n, which is n is the identity element. So, this is the identity element of this G modulo n, okay. So, this is something I will leave it to verify. And then if you take any Gn inverse, so that is exactly G inverse capital N. So, this is going to be the inverse of Gn inside your G modulo n, okay. And associativity comes for free from associativity comes for free from the associativity of capital G and well definedness of product. Okay. So, associativity is indeed comes for free from the well definedness of the product, and identity is nothing but this coset corresponding to the identity element of capital G is the identity inside G modulo n, and then the inverse of each this coset is nothing but G inverse capital N. So, these things actually verifies all the group laws of this G modulo n with respect to this product. So, that makes this G modulo n is a group, okay. So, now if this G modulo n is a group, so then it is easy to verify the quotient map that you have from G to G modulo n sending G to G capital N is indeed a group homomorphism. So, this is a group homomorphism. So, this is called quotient map. So, this is called quotient map or quotient homomorphism, and kernel of this map is exactly equal to capital N. So, this is something one can check immediately. Okay. So, the kernel is exactly the capital N. So, in particularly, so n is normal, that implies n is kernel of this quotient homomorphism. And if you go back to the definition, you can see that any kernel of any homomorphism is indeed normal subgroup. That is something we verified. So, that means we proved that 4 implies 8 and 8 implies 1. So, that completes the cycle. So, that proves all these characterizations are all equivalent. Okay. The definition 6 and 7, they are immediate from the definition. Okay. And 5 we verified on the way, because we need to verify that the product that we have defined is indeed well defined product. Okay. And that makes this G modulo n is a group, and that makes that this n is a kernel of this quotient map. Okay. To complete the cycle, we verified that kernel of any group homomorphism must be actually normal subgroup. So, this completes all the characterizations. Okay. So, I will stop here, and then we will actually see some examples. So, later using these characterizations in the next class, and we also see some examples of factor groups or quotient groups. Thank you. I will stop here.